All right, let's get started. This is going to be the first of two pre-recorded lectures that we're going to be having here soon. This lecture is going to be continuing the in-class discussion that we're going to have on gross and net area. So on Wednesday, we're going to have a lecture discussing how to compute how to compute gross and net area for parallel bolt paths, or essentially whenever you have a connection where the bolts are arranged in a grid-like fashion. And what we're going to do today is continue that discussion and ask, well, what happens if the bolts aren't arranged in a grid-like fashion? So what that's going to require is, first off, let's make sure that we recap what's going on with the expression for net area so far. So right now, this is sort of our expression for computing net area. And what we do is we take the gross area and we subtract from that the area lost due to the presence of bolt holes, which for now is just going to be the diameter of the hole in question times the thickness. And that should be something that we're all familiar or hopefully understanding after the previous lecture, that we're not taking, pi r squared or pi d squared over 4. What we're doing is we're taking the diameter times the thickness, because we're looking at it from a cross-sectional perspective. Now, the diameter of the hole, in order to compute that, what we're going to be doing in the class is taking the diameter of the bolt and adding 1/8 of an inch. I say that's what we're doing in class because in class we are dealing only with standard size bolt holes. So we add a 1/16 of an inch to the bolt diameter for erection tolerance. So in other words, if I have a 3/4 inch diameter bolt, I add a 1/16 of an inch to that diameter to actually drill the hole. So that's what I mean by erection tolerance. But then we ask how much of that material around the hole is effective in transferring stress to the rest of the member. And we say that we're going to add a 1/16 of an inch on top of that to account for that little bit of damaged material around which the hole was either drilled or subpunched or something like that. Now, this formula only works for grid-like bolt patterns. We're going to need to modify this for staggered arrangements through the use of what are called stagger factors. Now, what I mean by that is I wanted to give you a clear picture of what I'm talking about. So in this instance, I'm talking about a situation where if I look at bolted connection configurations, I'm talking about situations, this is what we dealt with last time, parallel grid-like bolt arrangements. I'm talking about today situations like this. Now, the first question I want to make sure that we're clear in understanding the answer of is, why would you do this? Why make it complicated? Why would you go through the process of staggering your bolt arrangement? Well, the short answer is it increases the net area, okay? And what we're going to see is that we have to account for these sort of diagonal failure paths that could happen in a potential net area fracture. And the way that we account for these diagonal paths is we're adding a certain degree of area. To put it simply, if I had a member that failed, let's say, perpendicularly versus, let's say, failing along this line, that's going to be a larger area, right? So think about this from an engineering perspective. If I can increase the net area, I can increase the strength. And if I can increase the strength or increase the usable strength for a given member, that can usually result in a more economical design. So there is a very practical reason for doing this. So for example, if you're designing a tension member and you have a member and it barely works, or it barely fails, I should say. If you're doing the analysis and you find that the member just isn't strong enough by just barely that much, maybe keep the member and stagger the bolts. And what you'll find is you increase the capacity to a usable place without having to increase the size of the member. So it's a way of getting an economical design with the member that you have. Now, whenever we're dealing with a staggered bolt arrangement, we have two complications. The first is, how do we account for the increased area along these diagonal paths? In other words, if I look at this member, instead of it failing, let's say, like this, we might have a failure path that goes like that, for example, and then we have diagonal failure paths to consider. So how do we account for that diagonal path? How do we account for the increased area along those paths? We're going to find a very straightforward way of doing that, and that's through what are called stagger factors, and we're going to see that here in a second. But the big one is, how do we account for multiple failure paths? What we're going to see both in this lecture and in the example that we're going to do is that for a given tension member, we might have multiple potential possible failure paths. Okay. Now, I want to make sure that we're clear that we only investigate failure in steel design primarily along the lead line of bolts. Okay. The easiest way to explain what the lead line of bolts are is, first off, so I have an image here. In this image, the bolts that are shaded yellow, these ones here up front, these are the lead line, okay? But if you want a simple way of identifying the lead line, imagine that you were standing, let's say, in the middle of this tension member. Let's say you were standing right here, and you were looking towards the bolted connection, and you had a flashlight in your hands, and you shone the flashlight towards the connection. What bolts would the light hit? Well, it would hit these 5 up here up front, okay? The idea is that as you are identifying potential failure paths, those failure paths which leave all the bolts intact are the ones that we're going to address from a limit state standpoint. So that's why we're only considering the lead line of bolts. And here in a bit, we'll talk about identifying those failure paths as well as the lead line. Okay, now going into the identifying potential bolt failure paths, I want to look at this connection, okay? So to give you the analogy, imagine we were looking at a connection on the left side. So you can see over here, I've got this sort of break line right here, which means that the rest of the member is, well, I guess I should point this way for the camera. The rest of the member is going along this side of the tension member. So if you were trying to identify the lead line, imagine standing like all the way over here, way off onto the slide, and then shining a flashlight towards the connection. The flashlight's going to hit bolts C, D, and E. So those are the ones that are along the lead line. Now, in order to identify possible bolt paths, so what we're going to do, and this is common among steel design, what we're going to do in this class and on homework assignments, is we're going to take the connection and sort of label it with potential failure paths. And what we're going to do is identify all of the paths that leave the bolts intact. Okay, so to kind of illustrate what we've got going on here. So, for example, let's look at this connection. Okay, and so I'm using the letters to make sure that we can identify the paths so we can all be speaking the same language. So I'm going to go ahead and give you one. Let's look at path BDG. Okay, so BDG is a potential failure path. Okay, because if I were to fracture along that path, that would leave all of the bolts intact, and it would completely separate the member. Okay, so that is a potential way that this member could fracture and literally split the member in half. Okay, that is a potential failure path. What you ought to do right now, if you're so inclined, is pause the video here right now and see if you can identify all other potential failure paths that could leave the member intact. Okay, all right, so let's see if we can identify those. Now, I'm going to give you one of them. Okay, let's look at A, C, D, G. Okay, now path A, C, D, G, if I just connect those lines, yeah, that leaves all the members intact, because if I were to cut the member, imagine taking a pair of scissors and cutting the plate along that red line, I could pull that member off, I could separate that member into 2 pieces, and I wouldn't have to snip any of those bolts in half. And you're going to see what I mean. If that's still a little iffy to understand, you're going to see what I mean here in a second. Okay, now let's go ahead and make sure, let's make sure that we keep our old path that we identified earlier. Let's make sure we keep that. So we have this path, A, C, D, G. Okay, another path could be sort of the mirror of that, and it could be B, D, E, F. Now, assuming that everything is symmetrical, we're going to assume that those paths are the same. And what I mean by that is we're going to be subtracting the same number of bolts and adding the same number of stagger factors. Okay, So that's not going to be really any different from a mathematical perspective. Plus, I think if you were to just look at the lines, I mean, imagine A, C, D, G, and B, D, E, F. All that is just taking the member and sort of flipping it like this. You're not really changing the path of failure, so it's not really going to result in a different answer. Now, one final answer that we could identify is this one right here, okay? A, C, D, E, F. Now, if you consider each of these paths are unique from a net area perspective. For example, BDG subtracts only 1 bolt from the gross area. These two paths subtract 2 bolts. This one subtracts 3 bolts. So from a net area perspective, these are the only ones that are unique. But you can also see the difference in stagger paths. So for example, if we look at path BDG, BDG has 0 diagonal paths, so we're not going to have to account for any stagger factors for path BDG. For this pair of paths right here, we've got 1 potential diagonal failure path, so we're going to have to account for that with a stagger factor. We're going to talk about stagger factors here in a second. Now, the final thing I want to get past before we move on from this slide is I said we only identify bolts along the lead line. Okay, so what do I mean? Well, let's look at this, and let's look at this path right here, this path. Is this a potential path along the lead line? Well, no, and here's why. Okay, so imagine, let me go back here. So imagine taking a pair of scissors, and imagine this was a sheet of paper, and actually cutting through the sheet of paper, just the plate, along that vertical line. Okay, now if you did that, yes, you'd cut the plate in half, but can you move it forward? Can you move it away? Well, no, because this bolt right here is still pinning that right side of the plate. So in order for this right half of the plate to translate to the right, that bolt D has to shear off. Okay, so that's the only path that, that's the only path along these notation that I put here on the plate that would not fail along the lead line. So we would not investigate this path because this path would not be leaving all of the bolts intact. We're going to look at bolted connection limit states later. Now you can look at this if you want. There is a way of investigating this path, but it will never control, and it'll be easier to explain that when we get into the math later. Now, one final point of clarification, okay, is that if we're looking at, let's say, this path right here, okay, the path is ACDG. You really would never have a path that looks like this. That path would never happen because think about, taking this plate and yanking it, yanking it in tension. It's going to want to fail along the path of least resistance. So why would the plate fail in this sort of like diagonal fashion here? If you're yanking on this in tension, it's wanting to fail perpendicularly. So all of the lines are going to want to be vertical unless they're fracturing from bolt to bolt, in which case you're going to have a straight line between those bolts because that's the path, or that's the least distance between those bolts. Okay, now let's get into now how to account for those staggered paths. Okay, now the way that we account for that is we use what's called a stagger factor. Okay, now this is the first time in this class that we are dealing with what's called an empirical equation, and it is not going to be the last. Okay, we are going to have a significant number of empirical expressions throughout this course, and so I want to take a step back and make sure that we all understand what an empirical expression is. So in engineering, we tend to deal with 2 types of models and equations that we use for practical design or practical applications. So the first are what I'd like to call mechanistic equations. And mechanistic equations are the ones that we can derive, right? We can take some physics, a couple derivatives, a couple of Newton's laws, and rearrange those, do some algebra, and boom, get an answer. A good example of mechanistic equations would be a lot of the stuff that we did last semester in CE 312 in structural analysis. In the end, we could tie a lot of that stuff to some basic Newton's law applications, principles of static equilibrium. a lot of it really sort of was very easily derivable. The stuff that we're talking about here, this isn't really so much derivable. This is empirical. And what empirical means is to essentially go down to the lab, do a lot of research and testing on, let's say if we're trying to account for staggered factors. So we do a lot of testing of tension members. We rip a lot of tension members apart, collect data on the geometry of the connection and the maximum load it could experience or it could withstand, and then figure out or sort of curve fit an expression that captures that data as closely as possible. So it's not really anything that you can derive. It's more of a curve fit, simplistic model that you can use to assess a complicated problem. A good example of that is the concept of a tension member. Okay, now in the land of tension members, we're going to deal with diagonal failure paths all the time. Okay, now later on when we start talking about shear lag, what you'll find is that the stresses around a connection are complicated. They're not easy. They're very discontinuous. They're very the stress contours around a given connection are very difficult to model. Okay, there's no real closed form simple equation that you can use to predict those. Okay, so there's really two ways of going about it. If you wanted, you could break out some expensive three-dimensional finite element analysis or some advanced computer modeling to try and simulate that behavior as close as you can, or you can try and come up with a simplistic means of assessing the problem. And that's where a stagger factor comes in. The short answer is that this factor accounts for the increased area along diagonal failure paths, and the best way of saying it is it's sort of close enough for government work. Okay. Now, so what we do is whenever we're computing net area and we see a diagonal failure path, so let's say we're looking at this connection and we're looking at, let's say, this failure path as an example. So the net area for that failure path would be the gross area. We would be subtracting 2 bolt holes, or if you wanted, you could say DE times the thickness. But we're going to add 1 stagger factor to account for that diagonal path right there. And that stagger factor is computed using the expression here. It is S squared divided by 4G times the thickness. Now I'll go ahead and tell you, if you look at this particular reference in the manual, I'm sure if some of you are studious in that regard, you're going to open the manual and it's not going to say S squared T over 4G. It's just going to say S squared over 4G. And some of you are going to go, wait, Dr. Mike, that's a typo. No, it's not a typo. It's just the way that the manual describes stagger. What the manual is saying is that for every diagonal path, you add S squared over 4G, but then that will just give you the increase along the path. You have to multiply by the thickness of the plate to get that in terms of area. So that's why I account for that here. Now, from a notation perspective, here on the slide, you see that the member is sort of aligned in a horizontal fashion, so we're applying the load this way. Whenever you're looking at a diagonal path, S is parallel to the applied load, so it's in the direction of the applied load. So S would be this dimension here, and G is perpendicular to the applied load. So G is that dimension here. So we call that the longitudinal spacing and the transverse spacing. Sometimes the transverse spacing is called the gauge. That's why we use G for that dimension and just S for longitudinal spacing. And then obviously the thickness. Okay, so now one note on stagger factors. I want to make sure that the bookkeeping is handled well. So this is not a practical example, but it's there to make the point. And this will definitely matter on your homework assignment. Okay. Now, whenever you're looking at these failure paths, okay, and this tension member is the same tension member. Like, you don't have to compute the net area on the left and then the net area on the right, because it's basically the same connection, just mirrored. Okay. So if we're looking at, let's say, the side on the left, okay, and if I was considering, let's say, this failure path, which is not the only one, by the way, and I'll talk about that here in a second. What you would not do is say, okay, this is G, this is this is S, and just have one big old stagger factor for the whole connection. So what you would not do is say the gross area minus 5 bolt holes plus one big stagger factor. That's wrong, okay? So this is dead wrong. Instead, what you're going to do is have a stagger factor for this, a stagger factor for this, a stagger factor for this, stagger factor for this. So the way that you're going to compute the net area for this member is it's going to be the gross area minus 5 bolt holes plus 4 stagger factors. And so a stagger factor for each of those diagonal paths. Okay. Now, one thing to consider is that that for this tension member, if you wanted to start identifying failure paths, there's actually more than one. Yes, it's true that this is a failure path. That's true. Okay. But another failure path is this one, or this one, or what about this one? Or, to keep it simple, just that one right there. The short answer is, whenever you're doing a tension member problem, is you really just sort of need to check all of them. And then checking all of them, you need to consider which one is the worst case scenario. And the easiest way to explain that is to get into our example that we're going to see here in a little bit. But I just want to make sure that we're all on the same page, that before I said, here's our expression for net area, but it is going to expand. This is now a more complete expression for net area. So now we can sort of say this is the formula for net area. It is the gross area minus the area lost due to the presence of bolt holes plus the inclusion of any necessary stagger factors dependent upon whether or not you need them. So if you have a grid-like expression or a grid-like arrangement of bolts, all those stagger factors go to 0. So it goes back to the original formula that we had before. But if we have a diagonal failure path, now we have something that's a little bit more robust. Now, one thing that I really haven't talked about is so for this lecture and for the previous lecture, I focused on bolted connections. Well, what about welded connections? Well, the gross area and the net area are usually the same. So for example, if we're talking about an angle that's been fillet welded onto a plate, you're not removing any material from that angle in order to make the connection. So the gross area and the net area are the same. So for welded connections, it's really easy. And one thing I will say, and I'll probably talk about this in much more depth when we get to connections, but we really don't use rivets anymore in most structural applications because they're unpredictable, they're kind of dangerous to install, and they're pretty expensive. I mean, we have riveted structures in the past, but high-strength bolts are much easier to use. Okay, so what we're going to do is we're going to look at the following example. And what we're going to do is we're going to compute the net area for this plate. Okay, and this is going to be the focus of our example. This is going to be the focus of our example in this video, or the rest of this video. Now, this is a new problem, but a lot of it isn't new. Okay, so what I'm going to do is I'm going to begin the problem by doing a lot of the stuff that I think you're familiar with right now. And then when we get into the new stuff, I'll tack that on at the very end. So I have a plate. It's 1 inch thick. I'm using 3/4 inch diameter bolts, which hopefully already that's triggering. Okay, it's 3/4 inch diameter bolts. So what's the effective hole diameter? Those types of thoughts that I want you to keep in the back of your head, because we're going to be adding to those types of decisions later on when we get into more comprehensive tension member analysis. Now, a couple things that may be a little new on this problem. So the first one is this right here. So what this is saying is that my longitudinal bolt spacing is 1 1/2 inches, but the term TYP is basically saying that's a typical dimension. In other words, instead of having to put a dimension here and 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 saying all these are 1 1/2 inches. Basically, it's just saying that dimension, you can just assume that's repeated along the longitudinal direction. So you'll see that every now and then on structural drawings, and in my class. I'll admit it's probably just a little bit of laziness. In the end, if you have a fairly straightforward connection, I don't think you need dimensions everywhere. The only thing I would say as an engineer is that when in doubt, put some dimensions on there. Okay. Now, in order to get into this problem, the first thing I'm going to do is I'm going to compute some base quantities. So the first thing I'll do is compute the gross area. Okay, so if we look at the plate has, if we look on the very right, so we have 2.5, 3.5, 3.5, 2.5. So the overall width of the plate is just that. So 2.5 and 3.5, and then just double that. So 2.5 and 3.5 is 6. Ooh, my! I don't know what happened there. Let's make that a little bigger. Okay, so that's 12 inches. So the thickness is also 1 inch, as was given in the problem. We can see that up here. So therefore, the gross area is just the width times the thickness, or 12 square inches. I'm gonna change that to that exponent. Looks awfully like a 3. Okay, I gotta believe that's pretty easy. Okay, now let's look at the bolt diameter, or more specifically, actually, let me rephrase it. Let's look at the hole diameter. All right, let's lower that a little bit so we're not squunching things up too much. We got plenty of room here. Okay, so the hole diameter. We're told in this problem that the bolt diameter is 3/4 of an inch. So therefore, the effective hole diameter is the bolt diameter plus 1/8 of an inch, in which case this is 7/8 of an inch. Okay, now one thing I'm going to go ahead and do right now is I'm going to go ahead and compute the area of the hole, which in this case is the diameter of the hole times the thickness. I'm not sure if I had done that for the grid-like lecture 4, because I'm recording this video before I do lecture 4 in class. But sometimes I'll want to compute the whole area first. Sometimes I'll just do it all at once. Usually I compute the whole area whenever I have a staggered connection. I say, let's just go ahead and do that now. So this is 7/8 of an inch times 1 inch, which is 0.875 inches squared. Let's not be so lazy up here. There we go. Okay, so we've got the gross area, we've got the hole diameter. Now let's handle our new stuff, some of our new stuff right here. The stagger factor. Okay, now let me go back up here to the connection. Okay, now remember the formula for the stagger factor is s squared t over 4g. Okay, now s squared t over 4g, remember t is the thickness, s is the dimension along the applied load, and then g is perpendicular to the applied load. So if here's the tension member, I'm going to be taking this tension member and I'm going to be yanking on it like this. Okay, so if we're looking at a given diagonal path, this dimension here, that's s. And this dimension right here, that's our G, that's our gauge spacing. So for this problem, S is going to be 1.5 inches and G is going to be 3.5 inches. Okay, so what I'm going to do is I'm going to go back here. So S is 1.5 inches and G is 3.5 inches. So therefore, the stagger factor is s squared t over 4g, which is 1.5 inches squared times 1 inch over 4 times 3.5 inches. Okay, and the nice thing about this is that, again, the manual just says s squared over 4g, but you incorporate the thickness so that you can add apples to apples. When you plug and chug all of this, so numerically, you're going to get something like 0.161, but the units are inches squared, okay? Because keep in mind, we have a inches squared, inches squared, inches squared. So that's what that inclusion of that thickness does. It allows us to treat that as apples to apples. Okay. All right, so hopefully that's pretty straightforward. Now let's actually get to the problem of actually identifying those net paths. Okay, so the first thing we want to do is we want to go back to, first off, identifying the lead line. So here's the member. I'm yanking on the member like this. So imagine me standing out here with my flashlight, and I'm shining a light this way. Okay, which bolts are we going to hit? Well, we're going to hit this bolt, and this bolt. Okay, so think, we're not going to hit this bolt right here, right? Because, you know, that bolt's going to get the light first. Okay, so those are going to be the bolts that we consider along the lead line. Okay, so just those green bolts. Okay, let me delete my little guy here so it doesn't get cluttered. Okay, so now what I'm going to do is, now that I have identified my lead line of bolts, I'm going to go ahead and start to label these. And I'm just using a labeling system so that when I'm discussing this on the video, we all sort of are able to relate to the same things. On the homework assignment that you all are going to get for this, the labeling has already been placed on the tension member, just so that we can all speak the same language when we look at the solution later. Okay, so what we now need to do is identify failure paths. Okay, and so what I mean by identifying failure paths is identify mostly perpendicular paths that go through these lead line of bolts that keep all of the bolts intact and fail the plate along the lead line. So a simple one would be ADF. Okay, so that's one. In other words, if that plate fractures in half along that blue line, that completely separates the member into two pieces, and it leaves all of the bolts intact. I can take that left part of the plate and freely translate it, and I'm not going to have to snap any of the bolts in half. So that's one failure path. Another failure path is B, C, D, F. Okay? So B, C, D, F would be failing like that, and then failing down. Again, if I snapped the bolt or the plate in half, if I fractured the plate along that blue line, B, C, D, F, it would completely separate the plate into two pieces, and it would leave all of the bolts intact. Now, similarly, I could also do A, D, E, G, but look at the dimensions. I mean, let's pay attention to these two paths right here. I have two diagonal paths in either of these options, but they both of those diagonal paths have the same S value, the same G value, and obviously the same thickness. So mathematically, they're not going to result in a different answer. So we can sort of group those together. Now, my third failure path can be sort of the one that subtracts all three bolts, B, C, D, E, G. And that's going to be one where we subtract 3 bolts and add 2 stagger factors. So let's actually get through the math on that. Let's take a look at the math and see what it looks like. Excuse me. So for net area 1, okay, so this is the one ADF. Okay, so let's look at path ADF and ask, how do we, what's the net area for that path? Well, it's the gross area minus the area lost due to the presence of bolts. That doesn't change. So how many bolts do we pass through along path ADF? We pass through 1. And do we add any stagger factors? Is there any diagonal paths along ADF? No. So there's our failure path. So okay, and so that's 11.25 inches squared. That is a particular net area for a particular path. Now we're just going to repeat this process for the other options. So let's look at net area 2. So let's look at path BCDF. Okay, so path BCDF, how do we compute net area? Well, we take the gross area and we subtract the area lost due to the presence of bolt holes. How many bolts do we pass through along path BCDF? We pass through 2. But path BCDF is different because path BCDF has one diagonal path. So we're going to add one stagger factor to account for that diagonal path. So that's going to be 12 square inches minus 2 holes plus 1 stagger factor. Because if you're failing along that diagonal path, that's a little bit of an increased area. So we always add stagger factors. Okay, now when you chug this out, you're going to get 10.411 inches squared. Okay, so let's just put a pin in that. Let's sort of keep that in our head, and then we'll continue calculating. Okay, so let's look at net area 3. So that's going to correspond to BCDEG. Okay, so what is BCDEG? So BCDEG, how many bolts do we go through in that path? Well, we pass through 3. How many diagonal paths do we encounter along that path? Well, 2 of them. One from C to D and then one from D to E. Okay, so let's chug this out. Then we'll say a couple things before we close this out. So notice how I'm adding 2 stagger factors, subtracting 3 bolts, and we're getting, when you chug this out, you're going to get 9.696 inches squared. Okay. Now, a couple things I want to say before we close out this problem. So the first thing I want to say is I want to go back to path 2, just to sort of make a point. Okay, when I was sort of verbally describing how we were going to compute the net area for this path, I was looking at path BCDF. So let's look at path BCDF. Okay, I have the gross area. How many bolts do I subtract along that path? 1, 2. All right, how many diagonal paths do occurs along BCDF? Just 1. So BCDF is the gross area minus 2 bolts, and I add 1 stagger factor. Now, what if I looked at path ADEG? Okay, well, what's the formula? It's the gross area minus 2 bolts, and then I add 1 stagger factor. So regardless of which path that I look at, I'm getting the same formula, so I'm going to get the same answer. Hence why I'm grouping those together. So if you're confused as to why I'm able to group those together and get the same answer, that's why. It's the same formula at the end of the day, so the math is going to work out and you yield the same answer. So that's the first point I wanted to make. Now the second point I wanted to make is I want to go back to the very beginning of the problem. The problem said compute the net area. It did not say compute 3 net areas. We have to compute the net area. So what does that mean? Well, what that means is that we have to consider the worst case scenario. So what is the worst case scenario? Which answer do we use? So more specifically, if let's go back to what we're using net area for. Ultimately, net area is going to be utilized as a means of computing capacity. Okay, we're going to be taking the net area and we're going to be multiplying it, let's say, by some stress or some safety factor example, in order to determine the amount of load that this member can withstand. Okay, so if I'm designing this member and I'm thinking to myself, what number can I hang my hat on? What number can I safely use as the net area in order to rely on that number for capacity? It's going to be the worst case scenario. What's the worst case scenario? The lowest one. Okay, because let's just keep it simple. Let's say that this steel can withstand 50 KSI in fracture. Okay, that's way oversimplified, and doesn't account for shear lag or factor of safety or anything like that. Some of the other stuff we're going to talk about later. But let's just use that as an example. Let's say that the steel can withstand 50 KSI. So what's the maximum allowable load in for this limit state? Well, it depends on which area that you use. Okay, so maybe it's 50 KSI times 11.25, or 50 KSI times 10.411. 50 KSI times 9.616. Each one of those is going to give you a load that this member can withstand. So which one do you use? Do you use the lowest one, right? Think, if I'm grabbing this member and I'm applying fracture, when is it going to fail? It's going to fail when that limiting stress reaches, the limiting stress times that area. It's going to be the lowest area, okay? So for the purposes of this problem, and I'm going to introduce you to some terminology in the land of structural engineering. I'm going to use the term governs. In other words, that's the value that's going to drive our calculations and designs moving forward. So whenever I use the term governs, it will typically refer to, if I'm computing resistances, I'm looking at the lowest resistance, or if I'm looking at loads, it's the highest loads. So as an example, if you remember the very first homework assignment, you were given some loads and you had to plug them into load combinations to get the worst case scenario. And on that assignment, you reported the maximum load. And I believe it was from load combination 2 in that homework assignment. And in that homework assignment, load combination 2 governed because it was the one that yielded the highest load. Just like with load combinations, you're trying to get the worst case load, which in that case is the maximum load. We're also looking at the worst case resistance, in which case it's the one that yields the lower resistance, in which case that's going to be net area 3. So for this problem, the net area is 9.696 or 9.70. That's going to be our answer. Okay. As I'm writing this out, one thing I will say for precision in your calculations. So if you look at the math that I did here on the proverbial whiteboard, I did everything to 3 decimal places. I tend to do that in class because I want to make sure that we're all arriving at the same answer. But past that, I really don't think there's any more precision that's necessary. And as you can see, when I reported my final answer, I just reported it to 2 decimal places. That's perfectly fine. I wouldn't get more loose than that because you do want to have some accuracy in your calculations, but know that I'm really not going to start hounding you over significant digits and things like that. So as long as you're getting your answer to within 2 decimal places for most problems, that's going to be good enough for the problems that we do in this class. Okay. One thing I want to do is very briefly review the homework assignment. So this is the homework assignment that that you're going to have for this unit. It's going to be due on Monday when this video goes live. So this is a somewhat similar plate, but I want you to determine the net area on this plate. So one of the things I'm going to tell you first off is there are much more potential failure paths. So I'll give you a couple as an example. So for example, BEFJ is a path. So is CDEFJ. Okay, there are a lot of potential failure paths on this problem. So part of this assignment is seeing whether or not you can identify all of them. Okay, now I'll go ahead and tell you, I know that as you're starting to do the math for this assignment, as you start to compute the net area for all of these paths, you'll start to notice a pattern, and you'll start to notice that you're starting to see what the answer is going to be at the end. And I get that. But again, this assignment is intended to just make sure that you're able to identify all those paths. So I want you to compute the net area for all of them. I think that you will probably make your life easier if you sort of do what I did for the example problem, which was go ahead and compute the gross area and then the whole area and the stagger factor first, and then go through and do the path determinations, because as you can see from this connection, a lot of those calculations are going to be fairly repetitive. So with that, that's all I have. In the next video, we're going to look at shear lag and slenderness. So we're going to sort of take it back to the limit state discussions that we talked about in class on Wednesday, and sort of make sure that we're completing the picture, as it were, and making sure that you get the big picture. Part of these initial few lectures are talking about the pieces related to tension members, and then we really start to get into it with some further analysis later. So hang in there with me. Next lecture, we're going to talk about shear lag and slenderness, but that's all I've got. I will see you all next time.